Thanks, Kuno. So I'm Shengyuan. So today I'm going to talk about private multitask learning formulation and methods. And this is a joint work with Stephen Wu and Virginia Smith from CMU. So I'll start with discussing a little bit about the setup in federated learning. So in federated learning, rather than collected a centralized data set, we let the data lives on the edge so that the privacy of the data is preserved. And the clients communicate the model or the model updates with the server, and they jointly try to train a model, and that could be deployed into the rest of the world. So there are two main challenges in federated learning. The first one, data could be heterogeneous across different clients. So one client could have 80% of the data belonging to one label, and the other could have 80% of its label data belongs to the other label. And the other challenge in federated learning would be you want to protect your own private data from being leaked to an untrustworthy server or to other curious other clients. So we call it client level privacy. So it is important to preserve client level privacy during the training of a federated learning model. In order to solve the first question, which is the data heterogeneity problem, one way to do it is to do model personalization. What does that mean? So instead of training one global model for potentially 1 million or a lot of different clients, we try to train a personalized model for each different client by letting them collaborate and leverage those global information to obtain a personalized model such that it achieves higher accuracy than both the pure global training and pure local training. One way to do model personalization in federated learning is by using this multitask learning formulation. So the traditional federated learning objective aims to find a single model W such that it minimizes the losses over all the clients and all the samples in those clients. While a general multitask relationship learning objective tries to find the best W, where the W is a weight matrix, where each row is a weight vector, and then omega, which is a relationship matrix, such that for each W, such that we want to minimize the loss on each WK, plus a regularization term that penalizes the relation between those different weights on different clients. Okay. So in this work, we try to provide a formal definitions of client level joint differential privacy for a general multitask learning objectives. And in particular, we studied the mean-regularized multitask learning objective and try to see what is privacy and convergence guarantee. And we also propose a scalable algorithm for private mean-regularized MTL and analyze its privacy and convergence guarantee. We also demonstrate empirically on 3 common federated learning benchmark datasets that our private MTL can actually provide improved privacy and utility trade-off. So now the first naive question is, what happens if we directly apply differential privacy to MTL? So consider a very naive DP-MTL algorithm that simply concatenate the personalized models at the end of each communication round, and then we do some clipping and add DP noise. As we can see on this feminist data set, the DP-MTL baseline is even worse than training a DP global method. Here, the global, we are using a federated averaging method. So DP-MTL is actually not giving us any benefits over training DP fed averaging. So what happens? Before I introduce how to correctly ensure client level DP for MTL, I'll start with this simple diagram that's showing what MTL is. So consider now we have k different data sets. In the setting of federated learning, we could think about this as k different clients. And some algorithm tries to jointly leverage those k different data sets and generate one model for each data set, which is W1 to WK. And here, W1 in WK in federated learning setting would just be a bunch of personalized data, personalized models. So what traditional DP requires us? Traditional epsilon delta DP requires us that if we are changing D1 to be a neighboring data set D1 prime, then the entire output of model W1 prime to WK prime should be indistinguishable to the original set of model W1 to WK. But this would require model of task 1 to have very little dependency on the training data of task 1 itself. Note that the purpose of preserving client level privacy is that we don't want the data for, say, D1 to be leaked to other clients, say W2 or WK, but not to himself, right? So we think a relaxed notion of privacy would be the following. So if we are changing a D1 to be a neighboring data set D1 prime, all the set of the output except this W1 should be indistinguishable to the output produced by D1 rather than D1 prime. So by enforcing this notion of privacy, just a glimpse of our final results on the feminist data set, our approach is called JDP-MTL. It not only outperforms DP-MTL a lot, it also significantly outperforms training a DP fed averaging model. And we'll go into details on more of those privacy utility trade-off and experiments in the later sections. So to formally begin with our setup, in this work, we specifically focused on the mean-regularized multitask learning objective, where for each client or each task learner, the local objective is not only the original empirical risk, but also in addition to that, we add a regularization term towards the average of those model. In that way, we are trying to leverage some global information in the local training so that we want to produce a model with higher utility and privacy and utility trade-off. And if an extreme case here would be if you set lambda equals to 0, this would converge, reduce to pure local training. And if you set lambda to be infinity, this would reduce to pure global training. So here we formally define what the joint differential privacy is, and this is first proposed in Kearns et al. 2014. So a mechanism is epsilon delta JDP if for all indices I and the neighboring data sets that only differs in the index I, we have that the output of two data sets except the ith index is indistinguishable to each other. A good property for using joint differential privacy in a multitask learning setting is that in this case, now every task-specific model, every client's model is still dependent on its own data, but at the meantime, it protects every task-specific model or client's model from the other clients, from inferring your privacy information. So we propose a private multitask learning solver, and at each communication round, the server first selects a subset of clients and broadcasts the global model, the current global model W tilde. And then upon receiving those global model, the client K tries to solve its local objective to update its personalized model WK. And this client updating method could be general. It can be any, you can pick any of your favorite algorithm to update the model. And in the case of fed averaging, it will just be run STD for some E local iterations to update the local model. After that, the server will collect and aggregates the model updates and apply clipping to the model updates. And after that, the server would add random Gaussian noise to the aggregated global model. So the last two steps is just subsample Gaussian mechanism. Since we are in a large federated learning network with, say, 1 million users, we cannot select all the milling users at every communication rounds because of you can experience network delay or some other issues. So basically, this is a subsample Gaussian mechanism. And this will complete one communication round. And after we train, say for some T communication rounds, we'll output the personalized model W1, W2 to WM when there are M different clients. So in order to show the privacy guarantee for our method, our privacy guarantee relies on this Bilbo lemma, which is proposed by Xu et al. 2016. Bilbo lemma basically says when you have a epsilon delta differential private mechanism and consider a set of function that takes in its original local data and this epsilon delta DP process as the input, then the composition of all of those functions is epsilon delta JDP. So basically, in our setting, we want to put the server will put the global model or any global component onto a billboard, and the client will grab information from that billboard, and we set this process for all the clients composed together is epsilon delta JDP. So we present our privacy guarantee for our algorithm in this theorem 1. This is an extension from the Abadi et al. Proof. From the bound of this bounding this sigma, we can show that the more tasks involved in the training, the smaller noise required to achieve the same privacy parameter. And we also want to emphasize that this formulation is general and it's not limited to MRMTL. Any MTL method that you have some global component and you want to put this global component onto your billboard, the similar theorem could apply to that setting. We also present a utility guarantee, which is basically a convergence guarantee for our algorithm in both non-convex and convex case. So in non-convex case, assume that the loss function itself is L smooth. And we are able to show that if algorithm 1 is epsilon delta JDP, the average of the gradient norm could be bounded by the MRMTL error, which is a linear, of linear convergence rate to a noise wall plus a private learning error. And if you can see over here, when we require more privacy, which means epsilon is smaller, this bound actually gets bigger, which means that there's a privacy utility trade-off here. If you want more privacy, you lose some utility. And similarly for the convex case, if we assume that the loss function is mu-Stirling convex and it's upper bounded by some constant b, we could show something similar. The private learning error is still of order all over 1 over epsilon square. So when we have more privacy, less utility. To verify or to experiment this, to look at this privacy utility trade-off in practice, we conducted some experiments on 3 common federated learning benchmarks for 3 baselines, including client-level private global model, where in our case we use a DP fed averaging, and a client-level private global model with fine-tuning, which is DP fed averaging with fine-tuning methods. For fine-tuning methods, we choose a bunch of different fine-tuning methods, including vanilla fine-tuning, elastic EWC or symmetricized KL. And we also compare our method with pure local training where there's no client-level privacy leakage at all. So we first show that on 3 data sets, we are observing something similar on the relation between communication rounds and losses and privacy parameters. So if we train more rounds, as the loss decreases, we got better utility, but at the same time, the privacy parameter could grow and to be very large, to be some value at 15, which becomes less useful in practice. To show this more directly, we also plot the relation between epsilon and test accuracy directly. For each epsilon, for each given epsilon, we need to tune the clipping bound gamma and the noise scale epsilon to get the best accuracy. So in this plot, we only plot the model with the highest validation accuracy given the fixed epsilon. From this set of results, we are seeing that given the same privacy budget, private MTL is able to achieve higher test accuracy on 3 data sets, comparing the blue line and the orange line. And at the same time, the dotted blue line and dotted orange line shows the non-private baseline for MTL and non-private baseline for Fed averaging. We can show that the MTL is able to retain or even expand advantage over Fed averaging in the private case, especially when epsilon is small. Yep. On the other hand, we also compare our method with global with fine-tuning and pure local method, and we plot them, and we choose the best fine-tuning method here and plot the relation between privacy and test accuracy. And as we can see that the JDP MTL with fine-tuning could get comparable or even better accuracies than global with fine-tuning, which is basically saying that personalization actually helps training for a small privacy budget. If you're looking at very small epsilon where epsilon equals 0.1, JDP MTL actually significantly outperforms global with fine-tuning. And also we can see that on all epsilon level, JDP MTL is able to outperform training in local model, which means learning from global information helps produce better prediction, even if we need to do it in a privacy preserving way. So some future works we are currently working on and extending our work includes we're trying to incorporate more sophisticated form of MTL beyond mean-regularization. This would include the first formulation of general mean-regularized, general MultiTask relationship learning formulation where we directly learn a relationship matrix. And we also want to decouple billboard lemma with JDP. So the current privacy guarantee relies on billboard lemma, and there could be cases where billboard lemma fails to yield good privacy utility trade-off, maybe vertical FL. And we also want to try to see how client level privacy could relate to example level privacy or local client level privacy and algorithm fairness, etc., in the context of federated learning. And that's it for my talk. Thanks for listening, and I can take the question right now.